this video, we're going to continue talking about sequential rationality, which is, again, the idea that in a game, it shouldn't be the case that you can say you're going to do something crazy in one branch of a tree, which keeps someone away from that branch of the tree, in order to get yourself, in order to get an outcome that you like more. Like, I want to go into the bottom branch of the tree instead of the top branch of the tree. I'm going to say I'm going to do something crazy up in the top branch of the tree, which makes the other person, if they believe me, go down to the lower branch of the tree. And then I don't pay a price for having said I was going to be crazy in the top part, so it can still be part of a Nash equilibrium. All right, so we want to continue with the idea of exploring how we go about solving games in that situation. So we're talking about sequential rationality. Okay, and the key idea that we're going to sort of require of decision makers in a sequentially rational equilibrium is that each player should maximize expected utility at every information set, regardless of whether that, or regardless of whether it is reached in equilibrium. So the basic idea is that we're going to require that decision makers at every information set make rational decisions at that information set. And so not only the information sets that are along the equilibrium path of play, but other information sets as well. So again, the idea is that all the players know, because of the common knowledge of rationality, that any information set that is reached, the other player is not going to play a dominated strategy. So like if you reach information set A, you're not going to do something that's stupid at A. So I'm not going to believe you're going to do something stupid at A. So it's basically it's this, it's the plain notion of the common knowledge of rationality that we've just discussed a lot, but we have to think of that notion of the common knowledge in the extensive form game, because we lost dynamics when we translated it into the strategic form. And so we're going to think of equilibria that are sequentially rational, where everyone is making rational decisions at every information set, as a way to recover what we lost in the translation. All right? So we're actually going to have to, we're still going to put games into strategic form. We'll find all the equilibria, but then we're going to believe more in the equilibria that are sequentially rational, that have everyone playing rationally in every information set, and believe everyone's playing rationally in every information set, rather doing that rather than being allowed to make crazy threats off the path of play. Okay? I already told you what a game of perfect information is, right? There's no dashed lines. It's every information set is a single node. In games like that, we apply a concept called backward induction, which we've discussed before. In games of perfect information, start at immediate predecessor nodes to terminal nodes. So basically look at the terminal nodes and the nodes that come right before them, eliminate dominated strategies then proceed to next predecessor node, etc. So we start at the back and work our way forward. All right, so here's an example of a game of perfect information. Player 1 chooses up or down. The game passes to player 2, who can choose A or B in that information set, C or D in this information set, and here it gets passed back to player 1, who can play E or F, and the payoffs are 3, 3, 2, 0, 1, 4, 5, 2, 6, 2. Okay? So, in this game, we start at, so if we start at a node, an immediate predecessor node to a terminal node. So for example, right here is a terminal node, the red dot. The immediate predecessor is this node right here, okay, the new red dot that I've made. And it's player 2's turn to act at that node. And so we ask the question, is there a dominated strategy? And the answer, of course, is yes. B is dominated. Right? If player 2 reaches that point, sequential rationality, in this form backward induction, right, is going to require that player 2 at that information set plays A. Okay? Here's another terminal node, the one ending at 3, 3. We go to this decision node, the immediate predecessor to that node. And here we have player 1 who faces the choice between E and F. Right? So player 1, if we reach that point, player 2 knows that player 1 is going to choose E, because 3 is greater than 2. And so that's a dominated strategy, or sorry, a dominated action at that information set. So we eliminate it. Okay? Next, we move to this node, an immediate predecessor to the one that we just worked with, and the one at 6, 2. Okay? At this node, we ask player 2, what are you going to do? Well, if player 2 goes down, she gets 2. And if she goes up, she's going to get a payoff of 3. If she plays C. Sorry, if she plays C, she'll get a payoff of C because she knows player 1 is playing E. Okay? So clearly this one is eliminated. D is an action that is dominated. And then, finally, player 1 faces U or D, and we can see the two paths that lead from U and D. In the first case, U, she ends up with a payoff of 1. In the bottom case, if she plays D, she ends up with a payoff of 3. So she prefers the payoff of 3, and thus she's not going to play U. U is sequentially dominated as an action. Okay? And so what we're left with is and so this whole chain, in fact, is destroyed because we can't reach that chain. Player 1 won't let us. All right? And that traces out the path of play. Okay? So we know that this path of play is going to take place. Okay? And so we know the Nash equilibrium that survives backward induction is at the first information set. So we're going to say the strategy for player 1 at the first information set, player 1 is going to play D, and at her second information set, she's going to play E. And at player 2's first information set, she's going to play A, and at the second one, she's going to play C. So this is the unique Nash equilibrium that survives backward induction. All right? So backward induction is a really easy concept to operate with. In games of perfect information where there's no dashed lines, you just work from back to front and everything goes through nice and easy. Okay? So we have a result. Every finite game with perfect information, meaning there's no dash lines in our game, in our extensive form game, has a for now we're going to call it a sequentially rational equilibrium. In a moment, we're going to introduce a specific kind of a more formal definition of sequential rationality, which is subgame perfect Nash equilibrium. So I'll just put that in parentheses. A subgame perfect Nash equilibrium, which we're going to define on the next slide. Okay. All right. And so it could have multiple equilibria. So in games where each player's action or each player has a strict best response at that information set, in games like that, the Nash equilibrium, the subgame perfect Nash equilibrium, is going to be unique. Okay. But there's some games where there could be a tie, and in the event of a tie, that could create uncertainty on the part of an earlier player. So if player 1 at a later point in the game has a tie between actions E and F, but player 2's payoffs are different at those two actions, then player 2 might not know what player 1 is going to do there, and so she doesn't know what the payoffs of her action is that leads to that information, to that node, and so she might do different things depending on her beliefs. All right. So if every action has a unique best response, then this subgame perfect Nash equilibrium will be unique. But in games where there's a tie between best responses, it's possible to have multiple Nash equilibria that are sequentially rational, that survive subgame perfection. Okay. One more thing I'd like to add about this game is that I'm gonna just grab another color real quick. Is that we want to still think about non-credible threats, right? So here, let's see, player 2 or player 1 at her second information set of the game, so up here, right, this little purple node, could have said she was going to play F, right? And that's a payoff of 2. If that, of course, would not be a rational thing to do if she actually reached that node. But imagine there's an equilibrium somewhere else up the chain. Like if player 1 wants to play up, but it can't convince player 2. Wants to convince player 2 to do that. So player 1 could say, "Hey, look, if you're gonna play C, I'm gonna play F, right?" And then player 2 believes her and says, "Well, if you play F, I'm going to pay off 0. But if I go down, I'm going to get a payoff of 2. And so, of course, if I believe you, I'm going to play. I'm going to play D. Okay. So this was a. non-credible threat to play F by player 1. Okay? Player 2 believes it, so she plays D, leading to a payoff of 6-2. Okay? And then, of course, player 1, knowing that she's going to, believing that she's going to get a payoff in that equilibrium, knowing she'll get the payoff in the equilibrium of 6, decides to go down instead of up. Okay? So we can think of another equilibrium, say U and F for player 1, and for player 2, let's say she plays A up top, and she plays D down below, is a Nash equilibrium, not subgame perfect Nash equilibrium. Okay? So, sorry, player 1's not playing, player 1's not playing U, player 1's playing D. Okay? So player 1 playing D and player 2 playing D, of course, means this game ends at 6-2, right? So that's the highest payoff player 1 can achieve in the game. So of course, DF is the best response for player 1. For player 2, it doesn't matter what she does at the top information set because it's unreached. So she could have also played DF, and she could have played BD up there. Again, BD seems crazy because player 2 is not doing as well at B as she is at A, but it doesn't matter because in this equilibrium they don't reach it anyway. So she could say whatever she wants up there and doesn't pay a price for it, right? So so we could say so is this one. Okay, so it doesn't matter what player 2 does at the top. Player 1 goes down, and if player 2 believes player 1 that she's going to play F at that information set, then she should play D instead of C, right? If you think someone's crazy and is going to do something that hurts both of you, then you should back off, right? And play D. And since player 2 plays D in these two equilibria, player 1 doesn't play a price for saying something crazy. So player 1 choosing strategy DF and player 2 playing AD or BD are both subgame perfect Nash, are both Nash equilibria. So if we wrote out the game in strategic form, this would be a 4x4 game. There would be 16 cells, right? We found just by looking at this, without even putting it into the strategic form, without even putting the matrix, we already found 2 other Nash equilibria, pure strategy equilibria, that are not subgame perfect. Okay, so so there can be a lot of equilibria in a strategic form game, but if there's an underlying extensive form that has a dynamic structure to it, which means that we play, one person moves and another person observes it, and then they move, etc. If we're in that kind of a situation, we can end up having lots of equilibria that aren't sequentially rational, that don't satisfy this subgame perfection condition, which I'm now going to define on the next slide. Okay, so what is this subgame perfection thing that I keep talking about? Okay, so first a definition. I have to define what a subgame is. And then I'll define what a subgame perfect Nash equilibrium is. Node X in a tree is said to initiate a subgame. This is where it was really important that I define what predecessor and successor nodes are carefully. Node X in a tree, by an extensive form of a game, is said to initiate a subgame if neither X or any of the successor nodes of X are in information sets that contain nodes that are not successors to X. Okay? An implication of that definition, that's not even worth saying, but I'll say it, but I won't write it. That an implication of this definition is that once players are in a subgame, it's common knowledge that they're in that subgame. Okay? So let's unpack this definition. So node X begins a subgame. First of all, X cannot belong to an information set with other nodes. Okay? So in other words, so this requires X is in its own info set. Okay? So if we have a game that starts like this with player 1 and this for player 2, a game like that, let me switch color. Not a subgame. Okay? So in that case, node X is said to initiate a subgame if neither X or any of the successor nodes to X are in information sets that contain nodes that are not successors to X. Okay? So X cannot. So this node that we have circled for player 2, that does not initiate a subgame because there's another node in the information set with this initial node. That's not allowed. Okay, so it has to start by itself, its own information set. Okay, and the other requirement is another implication of that definition. The subgame can't split info sets. So I'll draw that one over here. We can't have a situation where, okay, that okay, this is not a subgame. Okay? Because this is the initial node of our subgame. This node is a successor to our subgame. But this node is in an information set that contains a node that is not a successor to the first one. That's the problem. All right, so by our definition above, the node marked at player 1, that orange spot right here, this node here, is a successor to the first node, to the one at the number 2, that node, but it's contained in it's in an information set that contains nodes that are not successors, that can't be reached from the initial node of the subgame. All right? So you can't, it has to start, a subgame has to start at its own information set, right? It has to be a singleton. It can't start on a dash line. And it can't split up any dash lines. It can contain dash lines on the inside, but it can't split up dash lines. Okay? And then it also has to contain all of the successors. Right? So, must. Oops. Sorry. I didn't realize I was paused. So I don't know exactly where I was there. So let me just recap what I wrote. So the third and final rule, the intuitive rule that we can derive from that definition, is that all the success. So for a set of nodes and branches to be a subgame, they must contain all successors to the initial node. In this game, this piece is not a subgame because it doesn't include this node over here. I'm sorry, because it doesn't include that part of the tree. So there's a node, these terminal nodes, that aren't included in what I'd circled in orange. So the whole thing, this is a subgame. There are other ones in that game as well. In fact, there's a whole bunch of subgames, but that one is a subgame. Okay. All right. And so what we're going to do now is look at some games and identify what are all their subgames, and then we'll talk about subgame perfect Nash Equilibria. Okay. In fact, for this game above, it's a game of perfect information, and every non-terminal node in a game of perfect information initiates a subgame. So each of those nodes, if I look at this node that I just colored in blue, that initiates a subgame, this one. And then if I look at this node, it initiates a subgame, which includes everything in blue. And then this node initiates a subgame, which now includes everything else in blue. And then this node initiates a subgame, this little one down here. And this initial node also initiates a subgame. We say that the entire game itself is always a subgame itself. All right? So every game has at least one subgame, which is the full game itself. But not all games have more than one subgame. All right? So this game actually has 1, 2, 3, 4, 5, 6 subgames. 1, 2, 3, 4, 5, 6. In perfect info games, all non-terminal nodes initiate a subgame. Okay. One more kind of practice example of just looking at a game and identifying its subgames. So, this is not going to be a game of perfect information. We want to give practice with games that are not. So here's a game. It starts with player 1. We move to player 2, A, B, and then we move to player 3, E, F, and then down here we move to player 2 again, which is C and D, and player 3 does not know at that point whether to play, player 1 played U and player 2 played B, or if player 1 played D and 2 played C. That's closed to player 2. She can't see which of those two circumstances that she's in. And then player 3 at that point is able to play G, H, G, H. Okay? Of course, there's also payoffs. Each of the branches that ends with nothing, there's payoffs there. I'm just not going to bother writing the payoffs out because I'm not going to solve this particular game for any equilibria. So don't worry about the payoffs. They're in the book. This particular game is in the book. I just want to look at subgames. Okay. So what are the subgames of this game? Well, here's a subgame, right? It starts at a node that doesn't have a dashed line through it, right? And it contains all of its successor nodes, so subgame, right? Okay. Does this node initiate a subgame? Absolutely not, because it is not in its own information set. There's another node in it, so immediately we rule it out, right? Because it has nodes that are not successor nodes. It contains information sets that are not all successor nodes. So this is a node that's in the same information set that is not contained in successors to that initial node, okay? And vice versa over here. Neither one of these can initiate a subgame. They split up an information set, okay? Does this node up here initiate a subgame? No, it does not, because it would split this information set here. So the idea is that if we try to box it, we can't help but cut up that dashed line. So if we cut up a dashed line, it's not a subgame, right? So definitely not a subgame. All right, well, what about this node here? Does that initiate a subgame? Well, it starts by itself. That's a good start, but all the successor nodes to this node, we box them, and by boxing all the successors to that initial node, we split an information set. So it does not initiate a subgame. And then finally, the whole game itself. The initial node initiates a subgame. So this game has two subgames. Even though it's a fairly large extensive form game, it only has two subgames. If this was a game of perfect information, there would be 1, 2, 3, 4, 5, 6 total subgames, including the full game itself. There would be 6 subgames. But because of that one information set, we go from 6 subgames down to 2. So information sets can really limit how many subgames we have. All right, so next, why do we even introduce this notion of subgame? Well, it's because we wanted to find subgame perfect Nash equilibria. I will call these S, P, and E. It's a strategy profile that specifies a Nash equilibrium in every subgame. Okay? And note that because we said the full game is also a subgame, and the reason that we want the full game to be a subgame is because of this definition, that means that every equilibrium of the full game is, I was about to say something incorrect. So a necessary condition for an equilibrium to be subgame perfect is that it's a Nash equilibrium of the entire game itself. So subgame perfect Nash equilibria are a weak subset of the set of Nash equilibria. So all S, P, and E are NE, but not all NE are necessarily S, P, and E. Okay? Again, since the full game itself is a subgame, then every subgame perfect Nash equilibria has to be a equilibrium of that subgame, which is an equilibrium of the full game, right? So to be subgame perfect, it has to be a Nash equilibrium over just a regular Nash equilibrium. But in addition, it has to implement a Nash equilibrium in every subgame as well. Okay? And so, of course, with games of perfect information, backward induction, so backward induction on games of perfect info implement A S P N E. Okay? So because every non-terminal node initiates a subgame, and we resolve from back to front each of those nodes as best responses, and used iterated dominance to get ourselves there, right? We knew that the person playing at the end would choose a best response, which meant the person before them knew that, so they could take that into account when they made their choice, etc. Okay? Backward induction on games of perfect information do implement a subgame perfect as defined here, which is where we got the result earlier on, where we said that every game of perfect information has an SPNE, has a subgame perfect Nash equilibrium. We hadn't defined it yet, but backward induction on games of perfect information will always implement an SPNE, and there always exists one in games of perfect information. There always exists at least one. Okay? Here, we can see, we can do one more game of perfect information, just a short one. Player 1 can choose U up or down. Player 2 chooses A, B. C, D. One, 5, 2, 0, 0, 6, 6, 2. Okay. This is a subgame, right? So that has to resolve an equilibrium. So of course the subgame will resolve by player 2 choosing A. Okay. This subgame has to be implemented in equilibrium, and it's a really simple subgame, right? But this one has to be implemented in equilibrium, which means that player 2 will choose C. Okay. And then this also has to be implemented in equilibrium, which means that player 1 knows that by playing up, she'll get 1, and by playing D, she'll get down. She'll get 0, sorry, so she's going to play up. So player 1 choosing up, player 2 choosing AC is unique SPNE of this game. Okay? But if we put this game into strategic form, maybe there's other equilibria. So player 1 can play UD, player 2 plays AC, AD, BC, BD. Remember, there's one a strategy is defined as one action at every information set, two actions for two information set for player 2, which means 2 actions in each strategy. Right? Don't forget that. So if player 1 chooses up, player 2 chooses A, we get payoffs of 1, 5. If player 2 chooses B, we get payoffs of 2, 0. And then if player 1 chooses down and player 1 chooses down, player 2 chooses C, we get payoffs of 0, 6. And D for both players gets us 6, 2. What are the Nash equilibria of this game? Well, the best responses, if player 1 plays U, these are the best responses for player 2, AC and AD. And if player 1 plays D, best responses are AC and BC. And then in each column, here's the best response, here's a best response, and best response. All right. So in this particular game, there is only one Nash equilibrium. In this game, all N, E, R, S, P, and E. So in some games, the Nash equilibria of the game are also subgame perfect, right? But in some games, we have some Nash equilibria, like the very first one we looked at. So that game was not subgame perfect. I'm sorry, not all equilibria were subgame perfect. If you remember going back to that very first slide, second slide, I guess. In this game, DF and AD were not subgame perfect Nash equilibria. This first one, DF-AD, is not a subgame perfect Nash equilibrium because player 1, in both cases, is threatening to choose F, but that F does not implement a Nash equilibrium of the subgame with the initial node circled in purple, the second move of player 1. Right? So that's a subgame, but player 1 was not choosing an equilibrium. Okay? And further, the information set at the top for player 2, the bottom equilibria has player 2 playing B there. Also, that violates subgame perfection as well, because it's a subgame that's not being played in equilibrium. Very simple subgame, just a one-player subgame, but nevertheless, every subgame has to be played in equilibrium. Every subgame has to have players with making rational actions under the common knowledge of rationality. Okay, finally, we move on to a game. We'll do a couple games, maybe two, that are a bit more interesting for subgame perfection. Oops, I'm going to go back to black. So let's look at a game like this. Player 1 can choose up, player or down. If he chooses down, the game is over. A little time passes and player 1 can move again. Chooses A or B. Then player 2 moves. X, Y, X, Y. Okay? Payoffs, 3, 4. 1, 4. 2, 1. 2, 0. Okay? Two subgames in this game. This one. And the full game itself. Both have to be played in equilibrium for a Nash equilibrium to be subgame perfect. Okay? So, we can show what the full set of equilibria are first, and then we can compare that to the subgame perfect Nash equilibria. So the full game can be represented in strategic form. Player 1 has 4 strategies: UA, UB, DA, DB. Player 2 can choose X or Y. Any outcome that involves player 1 choosing down gives a payoff of 2, 6. And if player 1 plays A and 2 plays X, that's 3, 4, 1, 4, and this is 2, 1, 2, 0. Okay? We look at the Nash equilibria of this game. Let's look at the best responses for player 2. a whole bunch, almost everything, right? And for player 1, here, and these 3. So we have 3 total pure strategy Nash equilibria, and now we want to identify which equilibria are subgame perfect. Okay? Well, let's create so we need a Nash equilibrium for the subgame, but you guys know how to find a Nash equilibrium of a game in strategic form. So we find the Nash equilibrium of each subgame in the strategic form. That's really all we do, okay? Each subgame is resolved in the strategic form and has to have a Nash equilibrium, and then that Nash equilibrium, what they're doing in the subgame, has to be part of the full equilibrium profile. Okay, so in the subgame, player 1 is playing A, player 2 is playing B, X and Y, and we have payoffs of 3, 4, 1, 4, 2, 1, and 2, 0. There are a little double underline exercise. Player 1 plays A, best response, best response, best response, and best response. So one equilibrium of the subgame. So all S, P, and E include A and X in the profile, which implies, or it also means that B and Y can't be part of any S, P, and E. Okay? And so, since Y can't be part of any S, P, and E, we have, if we look at the Nash equilibrium of the full game, U, A, and X is S, P, and E, right? Because A is played, X is played, and it's also an equilibrium of the full game. But the other two equilibria, D, A, Y, and D, B, Y, are not S, P, and E. All right. So this game, and I'm just worried about the pure strategies here right now. We have one SPNE in pure strategies, but the other two pure strategy equilibria are not subgame perfect Nash equilibria. Okay, because they don't include equilibrium play in every subgame. Okay, so we'll look at one or two more games. Maybe one game, but I'll add two twists to this game, and we'll resolve them both at the same time. Okay. All right. So pretty big game. We have A, B for player one, C, D, C, D, E, F, E, F. And for player two, let's make it X, Y, X, Y. Okay? And so from there, you can already fill out your matrix. Well, you can create the matrix. You can't fill it out. I haven't given you payoffs yet. But you should be able to translate that into... whoa. Yeah, you guys hopefully were going to scold me. I have to... I didn't make that two different information sets. And I'm not going to put a dashed line there. Otherwise, the whole game would be... the only subgame would be the full game, and then every Nash Equilibria would be subgame perfect, so I don't want that to happen. So I want these to be two different numbers. Let's call it, here, let's just, we'll change those up here too. Let's make this W, X, Y, and Z. Okay? So player 2 is going to have 4 strategies available, and player 1 is going to have 8 strategies available. Again, we're looking at a strategy is 1 action at every information set. Player 1 has 3 information sets, 2 actions per information set. So it's going to be 2 to the third is going to be how, 2 times 2 times 2 is how big the strategy space for player 1 is. All right, so it's going to be a big game. 8 by 4. W, Y, W, Z, X, Y, X, Z. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. A, C, E, A, C, F, A, D, E, A, D, F, B, C, E, B, C, F, B, D, E, B, D, F. I can't tell you how many people take the final exam and can't do that, which is a killer, right? So I might give you this question, I might give you a description of a game, ask you to put it into the extensive form. So you just put it to the thing on the left, right? You take the description, put it into the extensive form. And then I'll ask you to put that extensive form into the strategic form. So the first question is from chapter 2, second question is chapter 3. Translate that extensive form to the strategic form, right? And then I ask you to find the equilibria of the full game in the strategic form, and then find the all subgame perfect Nash equilibria of the game, right? So it's a bunch of questions. Paragraph description, translate it to extensive form, translate that to strategic form, solve for the equilibria, maybe solve for rationalizable set, solve for subgame perfect Nash equilibria. Basically, you can ask a question from virtually every chapter on that same game. And if you set it up and you can't take the extensive form and put it in the strategic form, you cost yourself a lot of points. Okay? Don't do that. Make sure you can translate it because it's not hard. Right? 1 action at every information set, every possible combination. The size, this is all in your notes from before, but the size of the profile of the strategy space for player 1 is the number of actions in each information set, and then take the product of those numbers. So it's 2 times 2 times 2 in this case, because every information set has 2 actions. So there's 8 of them. You can't go wrong. If you know how to do this, it's impossible to make a mistake. Okay? So now I got to make some payoffs, and I want to think about some interesting payoffs. What interesting payoffs can I make? Let's see. I want to. I'm doing this on the fly. Sorry. So I want the bottom. So obviously, I'm sorry. We have 3 subgames. I'll circle those a while. 1 subgame. A second subgame. Plus the full game itself, which I drew over to the right. I don't want to circle the whole game because it'll get too messy, okay? But there's 3 subgames. And a subgame perfect Nash equilibrium has to be an equilibrium in each of those 3 subgames, okay? Has to implement an equilibrium in each of the subgames. All right, so the bottom game, I want there to be a unique Nash equilibrium of the subgame. And the top one, I want there to be 2 pure strategy equilibrium and 1 mixed strategy equilibrium between them. And then we'll know how to deal with the total set of subgame perfect Nash equilibrium, and then that'll be as far as you need to go with extensive form games and how to find subgame perfect. This will have all the bells and whistles in it, this particular game. Okay? So in this bottom one, let's make it resolve really. Well, let's see. Let's make player two have a dominant have a dominated strategy. Let's say Z is dominated. So I'm gonna have player two getting 2 here, 3 up here. I'm gonna have player 2 getting 4 here and 1 here. Okay, so clearly player 2 in this game with those payoffs is going to play Y no matter what because Z is dominated. So there is no equilibrium of the full game that has player 2 playing Z. If player 2 plays Z in any of the Nash equilibrium, it's not going to be subgame perfect. Okay? What's player 1 going to do? Well, she doesn't know let's say she doesn't see what action player 2 takes, but through common knowledge of rationality, she's going to know that Z is dominated. Okay? So she knows that player 2 is going to play Y, and so if player 2 is going to play Y, and this is 5, and this is 4, we know that player 1 is going to play E, regardless of what the payoffs are down here. We can make this a 2, and this a 6. Doesn't matter. Player 1. So anyway, so this is me thinking out loud as a teacher. But I think that thought process might help you. So let's just translate this game real quick into the strategic form and verify that it has a unique equilibrium. Let's see, player 1, player 2. If player 1 can either choose E or F, player 2 can choose Y or Z. EY results in 5, 3. Y for player 2 and F for player 1 results in 4, 4. ZE results in 2, 2. And here's 6, 1. And we'll do a little underline exercise. If player 1 plays E, player 2 plays Y. If player 1 plays F, player 2 plays Y. So indeed, Y is a dominant strategy. Z is dominated. And then if player 2 plays Y, player 1 plays E. And if player 2 plays Z, player 1 plays F. But player 1 knows that player 2 never plays that one. Here's the unique Nash equilibrium. So F and Z can't be part of any S, P, and E. Can't be. Okay? All right. So, yeah. And so in this game, at the top, let's make it a game that has a couple of different equilibria. So let's see. Let's say let's make this a 0, 0. Let's make this a 4, 4. Let's make the top one let's see, 6, 2. And let's make this one a 2, 6. All right. Those numbers, again, I'm kind of doing this off the top of the dome, but that's a hawk-dove game with double the payoffs, I think. Somehow I just erased a bit of my matrix up here. Okay, so I'm just going to look at the sub-game, at the Nash Equilibria, the sub-game, and then we'll fill in the full game. 1, 2. Player 1 can play C or D. Player 2 can play W or X. This one's 0, 0. WD results in 6, 2. XC is 2, 6. And XD is 4, 4. Okay. Where are Nash Equilibria? If player 1 plays C, player 2 likes X. That's not what I want. Wait, if player 1 plays C, player 2 plays X. And if player 2 plays X, player 1 plays D. If player 1 plays D, player 2 plays X. Yeah, that's not the payoffs that I want. All right, sorry about this. Let me change that up. So I want to switch these. I want this one to be 6, 2, and 2, 6. I think so. I'm gonna have to change the game. I think I want that one to be 6, 2, and this one to be 2, 6. So if player 1 plays C, player 2 will play X. Player 2 plays X. Player 1 plays C. And if player 1 plays D, player 2 plays W. Player 2 plays W. Player 1 plays D. Yeah, that's the game I want. So the top is 0, 0. XD is 4, 4. I want CX to pay 6, 2. Yeah, so I just need to switch these two around. Sorry about that. So CX, 6, 2, and this one's 2, 6. Okay, so now that game gives us the game below, and this game below has 2 pure strategy equilibria, okay, and a mixed strategy Nash equilibrium. What's the mixed strategy equilibrium? Well, if we make that Q and 1 minus Q, if player 2 is mixing, what makes player 1 indifferent? Well, it's if 0Q plus 6 times 1 minus Q equals 2Q plus 4 times 1 minus Q. So 6 minus 6Q equals, this is going to be 6 minus 4Q. So we're going to get 2Q, no, that's, I made a mistake somewhere. Oh, sorry, all kind of crap. 0 times Q, 6 times 1 minus Q. This should be a 2Q. And a 4 times, okay, cool. So let me do this. So this is 6 minus 6Q is equal to 4 minus 2Q. So this is going to give us 4Q equals 2, Q equals 1/2. Okay, all right. And obviously that's going to be true for player 1 as well. So sigma 1 equals 1/2 1/2, and sigma 2 equaling the same thing is also a Nash equilibrium of the subgame. Okay, now let's fill in the whole game. So there's a lot to fill in here. Let's see. If we play A and end up in WC, we get 0, 0. So these are all W0. If we play A and end up at WD, we end up at 2, 6. If we play A and end up at XC, we get 6, 2. And if we play A and end up at XD, we end up with 4, 4. And the bottom subgame, essentially, if player 1 plays B, right? If we end up at Y for player 2 and E for player 1, we get 5, 3. If we have Y and F, we end up at 4, 4. If we have Z and E, we end up with 2, 2. And if we end up with Z and F, we get 6, 1. Okay, and let's just look at these Nash Equilibria. I'm just going to underline all the best responses. And in the columns, we get this one, this one. Columns, we get this one, this one. This one, this one. And this one, this one, this one, this one. So unless I made any mistakes, these are all the pure strategy Nash Equilibria. Of course, there's also going to be some mixed strategies in there, but let's not worry about those for now. All right, now, what is subgame perfect? What does a subgame perfect Nash Equilibria look like? Well, we know the bottom game, we know the payoff, right? We know this bottom game ends up with 5 for player 1 and 3 for player 2. So we know that how that ends up, right? Because any so if play and why is that important? Well, player 1 knows that if she plays B, she's getting a payoff of 5. If player 1 is getting a payoff of 5 down in the bottom, and this would be equivalent even if the game B, even if B was out, a strategy out, and there was no subgame after it, it was just a payoff of 5, 3, it would be the same thing. Because of the common knowledge of rationality and because of subgame perfection. Player 1 knows that subgame will be played in equilibrium, so she knows that if she plays B, she's going to get 5 for sure. So on the next page, I'll just write that down. Player 1 knows her payoff in bottom subgame is 5, so she'll play B if the equilibrium of top subgame, if equilibrium pay of top subgame is so she'll play B if the equilibrium pay on the top subgame is less than 5. Play A if pay in top subgame is greater than 5. And I should say these are if the expected equilibrium payment. If expected equilibrium payment. Okay? So player one knows, so going back, player one knows that if she goes B, her payoff is for 5 for sure. So if there's an equilibrium in the top where she is going to get more than 5 in that equilibrium, well then playing A, playing the top subgame in the equilibrium that gives her a big payment, and then playing the bottom subgame in equilibrium, that's going to be subgame perfect. But it's also going to be subgame perfect if the top subgame is played in equilibrium that gives player one less than a payoff of 4, and so she plays B, and then the bottom is played in unique equilibrium. So there can be multiple subgame perfect Nash equilibrium depending on what the payoffs are. Okay? So, for example, CX is a payoff of the top that gives player one a payoff of more than 5, right? CX in top subgame gives player one payoff of 6, okay? Which is greater than 5. And so, now we can put together a subgame perfect Nash equilibrium. Player one plays A, and the other one is played in CX, right? So let's kind of put this information together. I'm just listing what has to happen, and then we'll put it together as a strategy profile. A and CX are played, and then in the bottom, we know that, let's see, player two is definitely going to play Y, and player one is going to play E, right? Because it has to be played in equilibrium in the bottom subgame. So Y and E. Y and E. And so our strategy is A, C, E, X, Y. That is subgame perfect. Okay? It implements an equilibrium at every subgame, right? It's implementing the CX equilibrium in the top subgame. It's implementing the EY equilibrium in the bottom subgame. And given those two subgame, the two equilibria of the subgame, player one is making the optimal choice in the first decision node. So in the final subgame, she's choosing A. Okay? And so that is the top, this is A, subgame perfect, Nash equilibrium. Okay? Now, what about the other equilibrium, the pure strategy equilibrium at the top? 2-6, right? The payoffs are 2-6. So the DW equilibrium. DW in top subgame gives player one payoff of 2, right? And so if that top is going to be played, right? If the top, so D and W are played in the top, if that one's going to be played in the top, well, the bottom one we know is still going to be played in the unique equilibrium. We know what equilibrium is going to take place down there. It's going to be the EY equilibrium, right? But in that case, player one's going to want to play B. So those are all the letters that got to be in play in our equilibrium. Okay? So player one choosing B, D, E. Player two choosing W, Y. Is a SPNE. Okay? So that one's going to be played in equilibrium. It's played in equilibrium in which player one does not do well. And so because player one does not do well in the top equilibrium, she chooses B, which implements the equilibrium in the bottom. Okay? So that one is also SPNE. Okay? Those are the only two pure strategy Nash equilibria that are also subgame perfect. So there were 6 total subgame perfect Nash equilibria. Only 4 of those equilibria are subgame perfect. The other 2 are not. The 2 of them are subgame perfect. The other 4 are not subgame perfect. So 2 of the 4 are subgame perfect. But there's a slew of mixed strategy Nash equilibria the full game. We're not going to deal with that. There's too many. But there is one more mixed strategy Nash equilibria, the subgame, that is subgame perfect, because the upper subgame could be played as a mixed strategy, the 50-50, right? Well, the expected payoff to player one of the mixed strategy of 50-50 is 3, right? The expected utility is 3. The expected payment of playing C is 0.5 times 0 plus 6 times 0, 6 times 0.5, right? Which is the same as 2 times 0.5 and 4 times 0.5. That's why we found 0.5 in the first place, okay? So in mixed strategy Nash equilibrium of top game, subgame, player 1 gets expected payoff of 3, which is going to make her play the bottom. Okay? So she's going to want to play the bottom. She wants to play B. We know how the bottom goes. It's going to be played as E. The bottom is played as EY, right? But then we also are going to be played in the mixed strategy of the first one, right? Of the top game, which is 50-50. Now this sucks that I don't have the matrix in front of me while I'm writing this out, so I'm going to have to do it on this page, okay? And then we'll just transfer it. So we need that the probability player 1 plays C or D is 0.5, okay? And that she plays B for sure. So the probability weight that she places on A is 0. So player 1 places no weight here, no weight here, no weight here, no weight here. And then she plays 50-50 weight on all the other strategies. Not on all the other strategies. Ooh, sorry. Because any of them that plays F, she doesn't put any weight on at all, because she never plays a strategy with F. So this gets 0 weight, this gets 0 weight, this gets 50%, and that gets 50%. All right, so that's our sigma 1. Okay, this whole thing is our sigma 1. And then our sigma 2 over here, let's see, player 2 never plays Z, right? Never plays Z in this equilibrium. So anything with a Z in it gets 0 weight. And the other two, the ones in which she's playing Y, get 50-50 weight. All right? And so that's the mixed strategy equilibrium on it. So that equilibrium profile, we can write it on the other page, but sigma 2, so let's get rid of that. Sigma 2 equals, I already forgot it, 1/2, 0, 1/2, 0. And sigma 1 equals, there's a whole bunch of zeros, so 1, 2, 3, 4 zeros, and then a half, 1, 2, 3, 4 zeros, and a half, 0, half, 0. Is also, this profile, sigma 1, sigma 2, is also a Nash equilibrium. And that's all of them. So the two pure strategy equilibria and this one, because these are the only equilibria of the subgames, right? And so the pure the overall Nash equilibria have to match these conditions. Okay, so that's a complicated game. I understand that. But it's if you understand the reasoning and can work your way up to the reasoning that allows us to say what are the 3 subgame perfect Nash equilibrium of that game, and also to be able to translate it and identify all the pure strategy equilibria of the game. And that game is so big, we're never going to want to find all the mixed strategy equilibrium. We're in good shape. You've understood the chapter. Awesome.